This example is a good one because the question is actually a little bit tricky in understanding what it's asking you. So it says, prove that the angle subtended by a diameter in a circle is a right angle. Now subtended talks about making an angle by two external points. Okay, so the idea, I've got a website here which actually shows us this. This shows you an angle subtended by a diameter. So this is the diameter in the circle, A to B, and this is a point here which you can move. And can you see what happens when you draw two lines off the ends of the diameter? They create an angle. So that's the angle subtended or made by the ends of the diameter. And the cool thing is you can move this around. And can you see there, even though the lines or the distance from A to that point and B to that point is changing, you see the point P is a right angle. Wherever it is, it's a right angle there, still a right angle. So the angle subtended, or you could effectively think of it as made, by the diameter, so the ends of the diameter in a circle, it is a right angle. You can see that from this experiment here, or this web page. But what we're going to do is actually prove that by using vectors. So I'm just going to copy this picture here just to help us out, and I'll put that into what we're doing here. Okay, so we're going to show this idea here. But what we'll do is we'll show that using vectors. So we've got 3 points, A, B, and P, and also the O, which is the center of the circle there. And we're going to prove that the angle subtended by a diameter in a circle is a right angle. So what we're going to do is we're going to show that this corner here is a right angle. And what I'm going to do is I'm also going to express that as vectors. So an easy way to do that, there's really two ways you could do that, but I'm going to do it just starting from P. So I'm going to create two vectors. I'm going to do one to there and another one, oops, I'll do the other one in red, one to there. So what we're going to do is show that the vector P to A is perpendicular to the vector P to B. Okay, so that is that the right angle subtended by diameter in a circle is this is a right angle. So what we need to do is really think about constructing these vectors out of what we have. And the easiest way to do that is to use position vectors all from the origin. So this is very familiar to what you've done before by creating vectors from an origin. So if we look at, I'm going to make 3 vectors here. This one, and this one. And I'm going to label them. This is O to A. This vector here is O to B, it's the point B. This is O to P. Now what do you know about these vectors? All of these vectors are a radius of the circle, aren't they? Half the diameter, so whichever way we go. So we know that from our diagram, the magnitude of O to A equals the magnitude of O to B, which equals the magnitude of O to P. They're all a radius, okay, of the circle. Now what we're going to do just to make life a little bit easier is I'm going to let O to A equal A. I'm just going to call it A, okay? So I'll put this in a different colour. Can you see here that this vector O to B is actually the same vector but just backwards? So we could call this negative A. So that implies that O to B equals negative A. And the other vector here, this is not in the same direction or parallel to A. So I'm going to have to call O to P something else. I'm just going to call this vector P. Okay? So we'll also let O to P equal P. So that implies, from this knowledge that we already have, we know that the modulus of A equals the modulus of P, yeah, because they're both a radius of that circle. So that's a bit of information that we have so far. So now what we're going to need to do for our proof is to prove this. Okay, so we have P to A. P to A can be shown in terms of the vectors that we've defined here. So P to A, that's this vector here, we could go backwards along O to P, and then we could go forwards along O to A. So we'd have negative O to P plus O to A. But we define these as P and A just to make things a bit easier. So this is basically negative P plus A. That's P to A, that vector there. And this vector here, P to B, so you could go backwards along O to P, and then you could go forwards along O to B. So that's P to B. So we've got negative O to P plus O to B. And we know that negative O to P, we just called it P. So that's P, A, and negative A, and this is negative A. So negative P minus A. So we've now defined PA and PB. So for our proof, what we're going to do is show PA and PB are perpendicular. So to show PA and PB are perpendicular, what could we do? We'll show that the dot product of those two things is 0. So we've got PA dot PB equals, remember PA is here, it's this expression. PA is negative P plus A, dot product with this angle, this vector here, P to B, so negative P minus A. Here we're going to do a bit of dot product action, negatives, they become positive, so it will be P dot P. This will be plus P dot A. This will be minus A dot P. And this will be minus A dot A. Now remember that A dot P equals P dot A. So the order doesn't matter. These two terms will cancel. So we now have the dot product as P dot P minus A dot A. Now to finish this off, we're nearly finished. This is very similar to the last worked example that we did. Oops. Do that again. Just bring it back. Copy and paste it over here. So now what we're going to do is identify, looking at that, you'll recall that the dot product of something with itself is the magnitude of that thing squared. And since we know from our diagram here, and we set it here, the magnitude of A and the magnitude of P are the same, we know that this is now going to cancel down. So we have, therefore, the dot product of P to A and P to B. So those two parts of the subtended angle is equal to 0. Therefore, P to A is perpendicular to P to B, and hence, go back to what you're trying to show, the angle, which is subtended by a diameter in a circle. Now the angle here is going to be APB or BPA, hence the angle APB subtended by the, and we should do the little angle sign, diameter, of a circle is perpendicular because the dot product of P to A and P to B is 0. So what have we shown? We've shown that this angle here, P to A, and this angle here, P to B, no matter where it is, and remember you could move this, it could be here, it could be here, it's still P to A and P to B, this doesn't matter where you put it, that angle has been shown to be perpendicular, P to A, P to B. So the angle APB is a perpendicular angle or a 90-degree angle, and we showed that by identifying what P to A and P to B are, by using other vectors, position vectors from an origin, the centre of the circle, defining those vectors, and then using the idea that, well, if these are perpendicular, then their dot product must be 0. And we went through and were able to show that. So the angle APB subtended by the diameter of a circle is perpendicular as required. And we should put that just to finish.